Imagine standing beneath an alien sky that has turned blue, red dust replaced by green valleys, thin carbon dioxide transformed into breathable air, rivers flowing where ancient channels once ran dry, Mars, once dead, now alive, forests spreading across Valles Marineris, rain falling on Olympus Mons, children playing in parks built into the walls of Jezero crater, never knowing this world was once frozen, silent, and utterly hostile to life. This is the dream, the vision that has captivated humanity for over a century. The promise that we could take a barren world and remake it in Earth's image, that we could become not just explorers, but creators, gods of terraformation, architects of planets. But what if that dream was actually a nightmare waiting to unfold? Tonight, we journey not to celebrate Mars's transformation, but to witness its destruction. To understand how the most noble ambition in human history, making a second world habitable, could become the greatest act of planetary violence ever conceived. We will explore the cascading horrors that lurk beneath every optimistic simulation, the geological awakenings we cannot predict, the atmospheric violence we cannot control, and perhaps most haunting of all, the genocide of life forms we haven't even discovered yet. This is not a story about whether we can terraform Mars. This is a story about whether we should, and what we would truly destroy in the attempt. Across the rust-colored plains of Mars, beneath frozen carbon dioxide ice caps and inside ancient lava tubes, there may already be life, fragile, microscopic, adapted over billions of years to conditions that would annihilate anything from Earth. What happens when we flood that world with our atmosphere? When we melt its poles and unleash water that hasn't flowed freely for eons? When we warm a planet that has been locked in deep freeze since before multicellular life existed on Earth? The answer is not inspiring. It is catastrophic. We will witness how atmospheric engineering could trigger dust storms so violent they would make today's planet-wide tempests look like gentle breezes. How melting subsurface ice could destabilize entire regions, causing landslides that dwarf anything in Earth's geological record. How introducing heat to a cold, stable world could wake volcanism we assumed was extinct, turning our paradise into a toxic hellscape of sulfur and ash. We will see how our water, the very substance we need for life, could become a weapon of mass extinction, dissolving minerals, releasing buried toxins, and flooding environments where Martian microbes might still cling to existence in the deep subsurface. And perhaps most troubling, we will confront the human factor, the ethics of planetary colonialism. The question of whether any species has the right to deliberately destroy an entire world's natural state, whether that world appears dead or not. Because Mars is not empty, it is ancient. It holds secrets about planetary formation, about the early solar system, about the conditions that lead to life itself, secrets that would be erased forever beneath our forests and oceans. Before we continue this journey into the beautiful horror of planetary engineering, I want to ask something of you. In the comments below, tell me where you are watching from and what time it is in your world. Are you drifting off to sleep or just waking? Are you on Earth, dreaming of Mars, or perhaps somewhere else entirely, pondering what it means to call any place home? Your presence here, across time zones and continents, reminds us that humanity is already a distributed species, even if we haven't left our birth world yet. Now settle in. Let your imagination drift not toward hope, but toward consequence. toward the realization that every great human ambition casts a shadow, and the shadow of terraforming stretches across an entire planet. Tonight, we do not ask how to transform Mars. We ask what we would destroy in the attempt, and whether some dreams are too dangerous to pursue. Our descent into this beautiful catastrophe begins now. Mars glows in the distance, a rust-colored beacon that has captured human imagination for centuries. Long before we had the technology to reach it, we dreamed of transforming it. The idea of terraforming Mars, of taking a dead world and breathing life into it, is perhaps one of humanity's most ambitious fantasies. It is a vision so compelling, so deeply embedded in our collective consciousness, that for many, it seems not just possible, but inevitable. A destiny written in the stars themselves. The dream of planetary transformation is not new. It stretches back through generations of storytellers, scientists, and visionaries who looked at Mars and saw not what it was, but what it could become. In the late 19th century, astronomer Percival Lowell gazed through his telescope and claimed to see canals on Mars, evidence, he believed, of an ancient civilization desperately trying to irrigate a dying world. Though his observations were later proven to be optical illusions, the seed was planted. Mars was not just a planet, it was a canvas, a place where life had existed, or could exist, or should exist. The line between observation and imagination had blurred, and in that blur, the terraforming dream was born. By the mid-20th century, science fiction had seized upon this vision with fervent passion. Authors like Kim Stanley Robinson crafted entire trilogies depicting the centuries-long transformation of Mars into a second Earth. These were not mere fantasies, but detailed blueprints disguised as novels, exploring the engineering, the politics, the ethics, and the timescales involved. Readers did not just consume these stories, they internalized them. Mars became synonymous with humanity's next chapter, the logical extension of our species beyond the cradle of Earth. What began as speculation evolved into expectation. Today, this dream has found its most vocal champion in Elon Musk, whose vision for Mars colonization has reignited public fascination on a scale not seen since the Apollo era. Musk speaks of Mars with the conviction of someone describing a destination already mapped, already scheduled, already inevitable. His proposal involves launching thousands of Starship rockets to Mars, establishing a self-sustaining city of 1 million people, and ultimately warming the planet by detonating nuclear weapons at its poles to release frozen carbon dioxide, triggering a runaway greenhouse effect. The planet would warm, the ice would melt, an atmosphere would thicken, and Mars would become, if not Earth-like, at least habitable enough for humans to walk without spacesuits. It is a vision delivered not with hesitation, but with the certainty of an engineer solving a technical problem. Mars is broken, and we know how to fix it. NASA's approach is more measured, but no less ambitious. Their concepts involve decades, perhaps centuries, of gradual atmospheric manipulation. Proposals include orbiting massive mirrors to focus sunlight onto the Martian poles, manufacturing greenhouse gases far more potent than anything on Earth to trap heat, or even redirecting asteroids to crash into Mars, releasing energy and volatiles trapped beneath its surface. These are not the ramblings of fringe theorists. These are peer-reviewed papers published by respected institutions, complete with calculations, simulations, and projected timelines. The message is clear. Terraforming Mars is not a question of if, but when. Not fantasy, but engineering at a planetary scale. Academic blueprints have proliferated across scientific journals, each offering variations on the central theme. Some scientists suggest introducing engineered microbes designed to produce oxygen and break down Martian soil. Others propose constructing colossal solar-powered factories that would churn out greenhouse gases continuously for decades. There are plans to thicken the atmosphere by mining Mars's subsurface ice, proposals to create artificial magnetic fields to shield the planet from solar wind, and models suggesting the introduction of hardy Earth plants genetically modified to survive Martian conditions. Each proposal is meticulously detailed, each backed by data and projections. Together, they form a narrative so persuasive that questioning it feels almost like resisting progress itself. But why? Why does this vision hold such power over us? What makes the idea of terraforming Mars feel not just appealing, but essential? The answer lies partly in psychology and partly in existential fear. Becoming a two-planet species carries a profound psychological weight. It represents transcendence, not just of Earth's gravity, but of our limitations as a civilization. For millennia, humanity has been confined to one fragile world, vulnerable to asteroid impacts, supervolcano eruptions, climate catastrophes, nuclear war, pandemics, and countless other existential threats. Mars offers something deeper than adventure. It offers insurance, a backup copy of humanity stored on another world. If Earth falls, if civilization collapses, if catastrophe strikes, there would still be humans somewhere in the cosmos, carrying forward the story of our species. This narrative taps into something primal, the urge to expand, to explore, to survive against all odds. We are descended from ancestors who crossed oceans on wooden ships, who ventured into unknown continents, who risked everything for the promise of new horizons. Mars is simply the next ocean, the next continent, the next frontier. To hesitate is to betray the pioneering spirit that brought us this far. Or so the story goes. The economic drivers are equally seductive. Mars is not just a destination, it is an opportunity, a virgin market, an entire planet's worth of resources waiting to be exploited. Rare minerals, frozen water reserves that could be converted into rocket fuel, vast tracts of land that could become the real estate of the future. Corporations and governments alike have begun to calculate the potential returns. If we can terraform Mars, or even partially transform it, property values could skyrocket. The first settlements would become legendary, historical sites comparable to Plymouth Rock or Jamestown. Early investors could become unimaginably wealthy. The economics of planetary colonization may seem distant, but they are already being discussed in boardrooms, venture capital meetings, and governmental policy briefs. There is also the undeniable appeal of legacy. To terraform a planet is to become gods in the most literal sense, creators of worlds, architects of atmospheres, engineers of evolution. The scientists, engineers, and visionaries who contribute to such a project would be remembered not for years or decades, but for millennia. Their names would be inscribed in history alongside figures like Galileo, Newton, and Einstein, not as observers of the universe, but as shapers of it. This is a form of immortality, a way to transcend the brevity of human life by participating in something that will echo through geological timescales. Pop culture has amplified this seduction to extraordinary levels. Films like The Martian and Total Recall, television series like The Expanse, video games like Surviving Mars, All depict Martian colonization as heroic, adventurous, and fundamentally good. These narratives focus relentlessly on human ingenuity, resilience, and triumph. Characters overcome impossible odds, build thriving communities, and turn Mars into a thriving world. The costs, the failures, the ethical complexities, these are either minimized or ignored entirely. We see astronauts planting flags, not ecosystems collapsing. We see dome cities sparkling under alien skies, not indigenous Martian chemistry being obliterated. The story we tell ourselves is one of creation, not destruction. This selective storytelling is not accidental. It serves a purpose. It builds momentum, generates funding, and creates political will. By focusing exclusively on benefits, the narrative becomes self-reinforcing. Children grow up dreaming of Mars. Students study engineering to make those dreams real. Investors fund startups developing Mars-related technologies. Governments allocate budgets for Mars missions. Each step makes the next seem more inevitable, more justified, more necessary. The dream feeds itself, growing larger and more concrete with each passing year. Yet within this seductive promise lies a dangerous assumption. That transformation is inherently positive. That change equals progress. That because we can reshape a planet, we should. The narrative of terraforming Mars rarely pauses to ask what might be lost in the process. It does not dwell on the possibility that Mars, as it exists now, might have value beyond its utility to human survival. It does not seriously consider whether we have the right to fundamentally alter another world before we fully understand it. These questions are not absent because they lack importance. They are absent because they complicate the dream. They introduce doubt where certainty is required to maintain momentum. The seduction is complete because it appeals to our best and worst instincts simultaneously. Our desire to explore and our fear of extinction, our capacity for innovation and our impulse to dominate, our hope for the future and our disregard for consequences we cannot yet see. Terraforming Mars feels inevitable, not because the science is settled, not because the ethics are clear, but because the story has been told so many times, in so many ways, that it has become part of our cultural DNA. We believe it because we want to believe it, because believing it makes us feel larger, more significant, more capable than we might otherwise feel on our small blue world, orbiting an average star. And so the dream persists, growing stronger with each passing year, gathering support from scientists, billionaires, storytellers, and dreamers alike. Mars waits in the darkness, silent and still, unaware that billions of minds on a neighboring planet have already decided its fate. The promise is seductive precisely because it asks so little of us in return. No sacrifice, no restraint, only the permission to do what we've always done, to take what we find and remake it in our image, to look at a world and see not what it is, but what we can make it become. The promise whispers that we are destined for Mars, that the red planet is ours for the taking. That transformation is not violence, but destiny. But as we shall see, every promise has a price, and the cost of transforming Mars may be far greater than we have allowed ourselves to imagine. The moment we decide to terraform Mars, the violence begins not with construction, but with transformation. Before a single habitat is built, before the first permanent settlement takes root, we must fundamentally alter the planet's atmosphere. This is not a gentle process. This is planetary surgery without anesthesia, performed on a world that has remained unchanged for billions of years. The methods proposed are not subtle. They are catastrophic by design, meant to shock Mars into a new state of being. Yet what sounds elegant in scientific papers becomes something far more terrifying when we examine the cascading consequences of atmospheric violence on a planetary scale. The proposals are dramatic, almost theatrical in their audacity. Detonate nuclear weapons at the Martian poles, vaporizing vast stores of frozen carbon dioxide to release greenhouse gases into the thin atmosphere. Construct massive factories across the surface, churning out perfluorocarbons and other super greenhouse gases, compounds thousands of times more effective at trapping heat than carbon dioxide. Redirect ammonia-rich asteroids from the outer solar system, crashing them deliberately into Mars to deliver both volatiles and kinetic energy. Each method carries the promise of rapid transformation, of accelerating what nature might take millennia to accomplish into a timeline measured in decades. But speed is the hidden danger here. Mars has existed in equilibrium for eons. Its thin atmosphere, its frozen water, its ancient regolith, all balanced in a delicate dance with solar radiation and the planet's weak magnetic field. When we introduce rapid change, we are not simply adding heat or pressure. We are destabilizing systems we barely understand, systems that may respond in ways no simulation has predicted. Consider the nuclear option first. The idea seems straightforward. Use the immense energy of nuclear detonations to sublimate the polar ice caps, releasing trapped carbon dioxide into the atmosphere. Each explosion would create a temporary inferno, temperatures soaring to millions of degrees, then rapidly cooling as the energy dissipates into the Martian air. The shockwaves would propagate through ice layers kilometers thick, fracturing ancient formations and releasing not just carbon dioxide, but trace compounds locked away since Mars lost its thick atmosphere billions of years ago. Yet the polar caps hold secrets. Layered within the ice are deposits of perchlorates, toxic compounds that have accumulated over geological time. When vaporized rapidly, these chemicals do not simply disperse harmlessly. They react. They combine with other atmospheric components in ways that could create cascading chemical reactions across the planet. Imagine clouds of chlorine compounds drifting through the awakening atmosphere, settling on the regolith, reacting with minerals that have oxidized over billions of years under harsh ultraviolet radiation. The chemistry becomes unpredictable, a planetary laboratory experiment conducted without safety protocols. The greenhouse gas factories present their own nightmare. To warm Mars significantly, we would need to produce truly staggering quantities of compounds like sulfur hexafluoride or perfluoromethane. These molecules are extraordinarily stable, which makes them effective at trapping heat, but also means they persist for thousands of years once released. Build enough factories, and we create an atmospheric composition that has never existed naturally anywhere in the solar system, a synthetic sky. As these gases accumulate and temperatures begin to rise, something unexpected happens in the Martian soil. The regolith, that fine rusty dust that covers the planet, is not inert. It contains peroxides, sulfates, and other reactive compounds created by billions of years of exposure to cosmic radiation and solar wind. When warmed rapidly, these compounds begin to break down, releasing gases we never anticipated. Suddenly, the atmosphere isn't just what we pumped into it. It's what Mars itself is exhaling after a multi-billion-year sleep. Some scientists have proposed artificial magnetosphere generation, massive electromagnetic systems designed to shield the growing atmosphere from being stripped away by solar wind. The idea has merit. Mars lost its original thick atmosphere, partly because its magnetic field collapsed early in its history. Without protection, solar particles steadily erode atmospheric gases into space. An artificial field could change that. But consider what this means for the planet's interior. Mars's core is partially solidified, its ancient dynamo long since cooled. Introducing powerful electromagnetic fields at the surface could induce currents deep within the planet, heating the mantle in unpredictable ways. We might intend to shield the atmosphere, but inadvertently we could destabilize geological structures that have been dormant for eons. Ancient fault lines might shift. Olympus Mons and the other massive shield volcanoes, silent for hundreds of millions of years, could stir. Not into full eruption perhaps, but into slow awakening, releasing gases from deep magma chambers, altering the planet's surface in ways we cannot control. The truly terrifying scenario is the runaway greenhouse. On Earth, we fear this outcome as climate change accelerates, the possibility that warming triggers feedback loops we cannot stop. On Mars, we would be deliberately initiating such loops, hoping to control them, trusting that we can stop the process at just the right moment. But planetary atmospheres do not obey simple linear models. They are chaotic systems, sensitive to initial conditions and prone to sudden phase transitions. Imagine this. We warm Mars enough that subsurface ice begins to melt. Water vapor enters the atmosphere, itself a powerful greenhouse gas. This causes more warming, releasing more water, accelerating the process. Simultaneously, carbon dioxide sublimates from the poles and from deposits in the soil. The atmosphere thickens faster than predicted. Temperatures rise beyond our target range. We attempt to halt the greenhouse gas production, but the processes we initiated have momentum now. Mars is generating its own warming through released volatiles. The atmosphere becomes too thick, too hot. Surface temperatures that were meant to reach Earth-like conditions instead climb higher. The water we hoped would form lakes and rivers remains vapor, creating a crushing, steamy atmosphere more reminiscent of Venus than Earth. We would have transformed Mars, yes, but not into a habitable world, into a different kind of hell. This is not mere speculation. Venus stands as a warning, a planet similar in size to Earth that experienced a runaway greenhouse effect long ago. Its surface temperature now exceeds 450 degrees Celsius, hot enough to melt lead, beneath an atmosphere 90 times denser than Earth's. The transition from temperate to inferno may have been gradual, but it was irreversible. Could we do the same to Mars? Could we create a second Venus, not through natural processes, but through hubris? The irony is profound and painful. Humanity considers fleeing Earth partly because we have damaged our own atmosphere, warming it through industrial emissions we struggle to control. Yet the solution we propose for Mars is to deliberately create a climate crisis, to warm a frozen planet using exactly the techniques we now recognize as catastrophic on Earth. We would become planetary engineers who learned nothing from our first atmospheric disaster, repeating the same mistakes on a new world, at an accelerated pace, with far less understanding of the consequences. Earth's worst atmospheric disasters offer comparisons, but they pale beside what we propose for Mars. The eruption of Mount Tambora in 1815 ejected so much ash and sulfur dioxide that global temperatures dropped, creating the year without a summer. The impact that killed the dinosaurs threw enough debris into Earth's atmosphere to block sunlight for years, collapsing ecosystems worldwide. These were catastrophes, yet they were temporary. The atmosphere eventually stabilized, life adapted or recovered. On Mars, we would be creating a permanent atmospheric catastrophe, one that unfolds over decades rather than days, but one that fundamentally alters a planet that has remained essentially unchanged for billions of years. The dust storms that already rage across Mars could intensify as temperature gradients shift. Winds could accelerate to speeds that make the surface even more hostile than it is now during the decades-long transition period. And perhaps most troubling, we would be conducting this experiment with no possibility of undo. Once we trigger these cascading atmospheric changes, we cannot simply reverse them. There is no planetary reset button. If we miscalculate, if the chemical reactions surprise us, if the geological responses exceed our models, we are committed to living with the consequences. Mars becomes not a second Earth, but a monument to our overconfidence, a scarred world that bears the marks of our atmospheric violence for geological epochs to come. The first catastrophe of terraforming, then, is not a disaster that might happen. It is the disaster we would choose to initiate, hoping to control forces that operate on scales beyond human experience, trusting simulations over the humility that planetary science should teach us. Mars rests in silence. Its volcanoes have not erupted for perhaps hundreds of millions of years. Its crust has cooled and settled into a deep, ancient stillness. The ground beneath our feet, should we ever stand upon it, is not simply dormant. It is frozen in time, locked in a geological slumber that has persisted longer than complex life has existed on Earth. But what happens when we attempt to warm a world that has been sleeping for eons? What forces might we awaken in our quest to transform Mars into something it has not been for billions of years? Terraforming Mars requires heat, immense planet-altering heat. Whether through greenhouse gases, orbital mirrors, or nuclear detonations, every proposed method involves raising the temperature of the Martian surface and atmosphere by tens, perhaps hundreds of degrees. We imagine this warmth melting ice, releasing carbon dioxide, thickening the atmosphere. We envision a gradual awakening, a gentle transition from frozen wasteland to habitable world. But Mars is not a passive canvas waiting for our brushstrokes. It is a geological system, complex and interconnected, and heating it rapidly may not awaken it gently. It may shock it into violent, catastrophic motion. Beneath the rusty surface of Mars lie volcanic systems that dwarf anything on Earth. Olympus Mons, the largest volcano in our solar system, rises 16 miles above the surrounding plains, nearly 3 times the height of Mount Everest. It is not merely tall, it is vast, covering an area roughly the size of Arizona. The Tharsis region, a volcanic plateau that stretches across a quarter of the planet, contains multiple shield volcanoes and has warped the entire Martian crust with its mass. These structures have been cold and inactive for countless millennia, their magma chambers solidified, their vents sealed with ancient rock, or so we believe. The truth is, we do not fully understand the interior of Mars. We know its core is partially molten. We have detected hints of recent volcanic activity, perhaps within the last few million years, a geological eye blink. We suspect that beneath the frozen exterior, pockets of residual heat may still linger, waiting. When we begin pumping energy into the Martian atmosphere, when we melt subsurface ice and alter pressure distributions across the crust, we are not simply changing the weather, We are fundamentally disturbing a planetary equilibrium that has existed since before our species emerged from the African savannas. Consider what happens when we melt the ice. Mars holds vast quantities of water frozen beneath its surface, mixed with soil and rock in a substance called regolith ice. In some regions, particularly near the poles and in mid-latitudes, this ice extends kilometers deep. As we warm the planet, this ice begins to melt. Water, unlike ice, flows. It seeps through cracks, dissolves minerals, lubricates fault lines. The ground that once supported itself through the structural strength of frozen water suddenly loses that support. The result would be catastrophic subsidence, massive sinkholes opening across entire regions as the ice beneath transforms from solid foundation to liquid void. We have witnessed smaller versions of this on Earth. When permafrost melts in Siberia or Alaska, the ground collapses, buildings tilt and fall, roads buckle into uselessness. On Mars, where ice deposits are far more extensive and the crust has been supported by frozen water for millions of years, the scale of collapse would be incomprehensible. Imagine valleys kilometers wide suddenly dropping hundreds of meters as their icy foundations vanish. Imagine the dust storms such collapses would generate, darkening skies for months, perhaps years. The melting of subsurface ice is not just a hydrological event. It is a geological catastrophe waiting to unfold. But the dangers extend beyond simple collapse. As we heat Mars, we create thermal expansion in its crust. Rock expands when warmed, contracts when cooled. On Earth, this cycle happens gradually, moderated by our thick atmosphere and active geological processes. On Mars, where temperatures could potentially rise by 50 degrees Celsius or more in a matter of decades, the thermal shock to the crust would be unprecedented in planetary history. Rocks that have been frozen for hundreds of millions of years would suddenly expand, creating stresses along every fault line, every ancient fracture, every weakness in the lithosphere. The result would be Marsquakes, seismic events that could dwarf anything in Earth's recorded history. Unlike Earth, Mars does not have plate tectonics to gradually release stress. Its crust is a single global plate that has been locked in place for billions of years. All that accumulated stress, all those frozen fault lines, could suddenly activate simultaneously. We might trigger a global seismic event, a planetary shudder that reshapes the surface, collapses canyon walls, and sends avalanches cascading down the slopes of ancient volcanoes. The ground itself would become unstable, unreliable, hostile to any structures we might hope to build. And then there is the volcanic question, the possibility that haunts every discussion of rapid Martian heating. Could we reactivate Olympus Mons? Could we awaken the Tharsis volcanoes from their ancient sleep? The question is not as absurd as it might seem. On Earth, we have observed that pressure changes can influence volcanic activity. The weight of ice sheets suppresses volcanic eruptions beneath them. When glaciers melt, volcanic activity often increases as the pressure on magma chambers decreases. Iceland's volcanoes have become more active as its glaciers retreat. Similar processes have been documented in other glaciated volcanic regions. Mars is covered in massive ice deposits, particularly at its poles. These ice caps weigh billions of tons, exerting pressure on the crust beneath. If we melt this ice, if we redistribute this mass through melting and evaporation, we reduce the pressure on whatever magma chambers might still exist beneath the surface. We do not know if there are still molten pockets beneath Olympus Mons or the Tharsis region. We cannot drill deep enough to find out, not yet. But if they exist, and if we release the pressure that has kept them contained for millions of years, we might see something unprecedented, a volcanic eruption on a scale that makes Earth's supervolcanoes seem modest by comparison. The eruption of Olympus Mons alone could darken the Martian sky for decades, filling the thin atmosphere we worked so hard to create with volcanic ash and gases. The lava flows could extend for hundreds of kilometers, obliterating any settlements in their path. And because Mars has lower gravity, eruption columns could reach higher into the atmosphere than anything possible on Earth, potentially injecting material directly into space. We would not be terraforming Mars. We would be creating a volcanic apocalypse that renders the planet uninhabitable for centuries, perhaps longer. History offers us cautionary tales, scaled to our small human perspective. We have triggered earthquakes through dam construction, through wastewater injection, through geothermal energy extraction. The 2008 Sichuan earthquake in China, which killed tens of thousands, has been linked to the weight of water in the Zipingpu reservoir. Fracking operations routinely trigger small earthquakes. We have learned painfully that disturbing geological equilibrium, even on local scales, can have devastating consequences. Now imagine those same principles applied not to a reservoir or an oil field, but to an entire planet. The scale of potential disaster becomes almost incomprehensible. Mars has been geologically stable for longer than complex life has existed on Earth. Its surface preserves features billions of years old, undisturbed by tectonics, unaltered by active geology. This stability is not weakness. It is a delicate balance, a planetary equilibrium achieved through the cooling and solidification of an entire world. When we propose to heat Mars rapidly, to melt its ice and thicken its atmosphere, we are not simply changing surface conditions. We are fundamentally disturbing a system we barely understand, gambling that we can control forces that have shaped worlds for billions of years. The geological awakening of Mars would not be a gentle stirring from sleep. It would be a violent shock, a planetary convulsion triggered by our hubris. And once awakened, Mars might prove impossible to calm again. We descend beneath the surface of Mars, into caverns and pockets of ice where the silence has remained unbroken for billions of years. Here, in the darkness beyond human sight, there may exist something extraordinary. Not monuments or cities, but life itself. Fragile, microscopic, ancient. As we contemplate terraforming this world, we must confront an uncomfortable truth. We may be planning the extinction of organisms we have not yet discovered. A genocide committed not through malice, but through ignorance and impatience. The question of Martian life is not science fiction. It is one of the most profound scientific pursuits of our time. Deep beneath the rust-colored surface, where temperatures stabilize and radiation cannot penetrate, conditions may exist that mirror the extreme environments on Earth where life thrives. Subsurface lakes of briny water, protected from the harsh surface conditions, could harbor microbial communities that have evolved in isolation for eons. These would not be visitors from Earth. They would be the descendants of Mars's own primordial biology, if such biology ever emerged. Recent discoveries have transformed this possibility from speculation into serious consideration. The Mars Advanced Radar for Subsurface and Ionosphere Sounding Instrument aboard the European Space Agency's Mars Express orbiter detected what appears to be liquid water approximately 1 mile beneath the southern polar ice cap. This is not frozen, dormant ice. This is liquid water existing under immense pressure, possibly enriched with salts that lower its freezing point. On Earth, wherever liquid water exists, life finds a way. Deep ocean vents, Antarctic subglacial lakes, water trapped in rock formations miles underground, all of these environments support microbial ecosystems. Why should Mars be different? The Martian meteorite, ALH 84001, discovered in Antarctica, contains structures that some scientists believe could be fossilized bacteria. While this interpretation remains controversial, it opened a doorway in our collective imagination. If life once existed on Mars's surface when the planet was warm and wet billions of years ago, could descendants of those ancient organisms have retreated underground as the planet cooled and dried? Could they still persist today in hidden refuges, adapted to conditions we can barely imagine? Terraforming Mars would obliterate these potential biospheres before we ever confirm their existence. The process would be catastrophic for subsurface life. Massive atmospheric changes would destabilize thermal gradients that have remained constant for millions of years. Deliberate warming of the planet would melt subsurface ice, flooding ancient caverns and disrupting delicate chemical balances. The introduction of gases to thicken the atmosphere would gradually seep into the ground, altering pH levels and creating toxic conditions for organisms adapted to Mars's current chemistry. Consider the violence of deliberate bombardment with comets or asteroids to release water vapor. Such impacts would send shockwaves radiating through the planet's crust, creating temperature spikes that could sterilize subsurface zones extending for hundreds of miles from each impact site. The very actions we would take to make Mars habitable for humans could render it uninhabitable for the life already there. But the most insidious threat comes not from our grand engineering schemes, but from something microscopic: contamination. Every spacecraft we send to Mars carries with it the ghost of Earth. Despite rigorous sterilization procedures, microbes cling to surfaces, hibernate in electronics, survive in places we cannot reach with heat or chemicals. Some organisms can endure the vacuum of space, cosmic radiation, extreme temperatures. They are biological stowaways, hitchhiking across the solar system. If Earth microbes reach Martian subsurface habitats, the result would not be coexistence. It would be conquest. Earth life has evolved in one of the most competitive environments in the known universe, refined by billions of years of evolutionary warfare. Martian organisms, if they exist, would have evolved in isolation, adapted to specific stable conditions without exposure to Earth's aggressive microbial strategies. The interaction would be analogous to European diseases decimating indigenous populations in the Americas. The local biology would have no defense. This contamination scenario becomes inevitable during terraforming. We would not be sending sterile robots. We would be sending humans, and with them, trillions of microorganisms. Every colonist would be a walking ecosystem, hosting bacteria, fungi, viruses, archaea. These organisms would spread into habitats, waste systems, eventually seeping into the ground. Once Earth microbes establish themselves in Martian subsurface environments, any native life would face an invasion it cannot survive. The ethical implications are staggering. We would be destroying an entire domain of alien biology, potentially the only other example of independent genesis we might ever find. Astrobiology seeks to answer one of humanity's deepest questions. Are we alone? Did life emerge only once, on Earth, or is it a common consequence of chemistry and time? Mars may hold the answer, encoded in the genetics of organisms clinging to existence in underground ice. If Martian life exists and shares biochemical similarities with Earth life, it could suggest panspermia, the exchange of life between worlds via meteorites. If it is radically different, using alternative biochemistry or genetic systems, it would prove that life can arise independently through multiple pathways. Either discovery would revolutionize our understanding of biology, chemistry, and our place in the universe. But terraforming would erase this knowledge before we could obtain it. The loss would be irreversible, a cosmic library burned before we learn to read. This raises philosophical questions that science alone cannot answer. Does undiscovered life have rights? Can we grant moral consideration to organisms whose very existence remains hypothetical? Traditional ethics struggles with this problem. We protect endangered species, but only after confirming they exist. We establish nature preserves, but only in locations we have surveyed. Mars presents a different challenge. We must decide whether the possibility of life is sufficient reason to halt our ambitions. Some argue that uncertain potential should not constrain definite human expansion. Others counter that destroying possibly the only other biosphere within reach represents such profound recklessness that no human benefit can justify it. The debate reflects deeper tensions in how we value discovery versus utilization, knowledge versus territory, restraint versus manifest destiny. Legal frameworks exist, though their enforcement remains theoretical. The Outer Space Treaty of 1967, ratified by over 100 nations, includes provisions for planetary protection. Article 9 requires that space exploration be conducted so as to avoid their harmful contamination and also adverse changes in the environment of the Earth. The treaty mandates that nations avoid contaminating celestial bodies and preserve them for future scientific investigation. The Committee on Space Research, known as COSPAR, has established planetary protection protocols that categorize missions based on contamination risk. Mars is designated a Category 4 target, requiring stringent sterilization for missions exploring regions where liquid water might exist. Terraforming would violate every principle of these protocols. It would be deliberate planetary-scale contamination, transforming preservation into destruction. Yet these frameworks were written for an era of robotic exploration. They did not anticipate permanent human settlement or deliberate planetary modification. As technology advances and Mars becomes increasingly accessible, pressure builds to reinterpret or abandon these protections. Some propose that economic and survival imperatives override theoretical concerns about microbial ethics. This tension reveals something uncomfortable about human nature. We are explorers and destroyers simultaneously. Our curiosity drives us to seek other worlds, but our presence threatens what we seek to understand. We celebrate the discovery of new species on Earth, while driving countless others to extinction through habitat destruction. Mars simply presents this paradox on a planetary scale. The tragedy is not that we cannot terraform Mars. The tragedy is that we might do so before answering the most important question. Before we remake Mars in our image, we must first discover what Mars already is. The scientific method requires observation before intervention, understanding before manipulation. Terraforming reverses this sequence, placing human desires ahead of cosmic knowledge. In the hidden depth of Mars, in pockets of ancient ice and mineral-rich water, there may be silence, Or there may be life, quietly metabolizing, reproducing, surviving. We do not yet know. And if we proceed with terraforming before learning the answer, we will have committed an act of destruction so complete that no future generation will be able to undo it. We will have silenced voices we never heard, extinguished possibilities we never explored, and answered the question, "Are we alone?" with the response, "We chose to be." This is not about preventing human progress. It is about ensuring that progress does not blind us to consequences we cannot foresee. The microbial massacre would be invisible, unintentional, and absolute. And unlike other mistakes we have made, this one cannot be corrected. Extinction, especially of an entire planetary biosphere, is final. What we destroy in our haste, the universe will not create again. Water on Mars is not abundant. It is not renewable. It is not waiting patiently beneath the surface for humanity to arrive and claim it. Mars holds water the way ancient tombs hold treasure, locked away, preserved across eons, finite and irreplaceable. Every molecule of water on Mars tells a story billions of years old. A story of rivers that once flowed, of lakes that shimmered beneath alien skies, of a world that knew moisture before Earth's continents had even formed. To terraform Mars is to consume this ancient inheritance at a rate that would make even Earth's most wasteful civilizations seem cautious by comparison. The water that remains on Mars exists primarily in three forms: locked within the polar ice caps, trapped as permafrost beneath the regolith, and bound within minerals in the crust itself. These reserves are not vast underground oceans waiting to be tapped. They are scattered deposits, frozen hard as stone, mixed with dust and salt, protected by the very coldness that has preserved them for geological ages. Extracting this water would require heating the soil, mining the ice, processing the minerals, all activities that demand enormous amounts of energy. And once released, this precious resource faces a threat more insidious than human consumption. Mars itself would begin stealing it back, molecule by molecule, into the void of space. Unlike Earth, Mars possesses no global magnetic field. This absence is not a minor technical challenge. It is a fundamental vulnerability that shapes the fate of any atmosphere we might create. Earth's magnetic field acts as an invisible shield, deflecting the solar wind, those streams of charged particles that flow constantly from the sun. Without this protection, Mars stands naked before the cosmic storm. Any water vapor we release into a thickening atmosphere would be subjected to a process called atmospheric escape. Solar radiation would strike water molecules with enough energy to break them apart. Hydrogen, the lightest element, would drift upward and be swept away by the solar wind. Oxygen might linger longer, but eventually it too would be stripped away, atom by atom, year after year, until the atmosphere we had worked centuries to build began thinning once more. Scientists have calculated the rate of this loss. Even with optimistic estimates, Mars would lose atmospheric gases at a pace far faster than natural processes could replenish them. Every ton of water we melt and vaporize would be participating in its own slow disappearance. The irony is profound. We would be mining ancient Martian water to create an atmosphere that the planet itself cannot hold. It would be like pouring water into a vessel with no bottom, watching it drain away even as we desperately try to fill it faster. The timescales might span centuries, but the outcome would be inevitable. Mars would become a world perpetually thirsty, dependent on continuous replenishment of resources that are anything but infinite. But atmospheric escape is only one dimension of the water catastrophe. The moment we begin industrial-scale terraforming, we introduce another: contamination. Mars's ice is pristine. It has been untouched by industrial pollution, by chemical runoff, by the countless synthetic compounds that humanity has scattered across Earth's water systems. The polar caps and subsurface ice represent perhaps the cleanest water in the solar system. Archives of Martian climate history preserved in crystalline layers. To terraform Mars would require massive industrial operations: nuclear reactors to provide power, chemical factories to process regolith, mining operations to extract resources, refineries to produce fuel and materials. Every one of these facilities would generate waste. On Earth, we learned this lesson slowly and painfully. Rivers became dumping grounds. Groundwater absorbed industrial chemicals. Microplastics infiltrated even Antarctic ice. We developed regulations only after the damage was done, and even now, we struggle to clean up the contamination of previous generations. On Mars, we would face the same pressures, but magnified. The rush to terraform, the economic incentives, the desperation to make the project succeed quickly before funding dries up or political will falters. All of these forces would push toward shortcuts, toward acceptable levels of contamination, toward the same rationalizations that have justified pollution on Earth. The pristine Martian ice would become laced with industrial compounds, radioactive isotopes from nuclear operations, and chemical residues from atmospheric processing. Consider what this means for any indigenous Martian life that might exist. If microorganisms shelter in subsurface ice layers or in pockets of liquid brine, industrial contamination would reach them long before we even confirmed their existence. We would be poisoning potential habitats before we fully explored them, repeating on Mars the pattern we have enacted across Earth's ecosystems. Develop first, discover what we destroyed later. The water that might harbour alien biochemistry would become an industrial slurry, its scientific value compromised, its biological potential extinguished. The parallel to Earth's water crises is impossible to ignore. On our homeworld, we face shortages not because water has vanished from the planet, but because we have rendered so much of it unusable. Aquifers are depleted faster than they recharge. Rivers no longer reach the sea. Lakes shrink into salt flats. We have learned that water scarcity is not just about quantity, but about quality, accessibility, and the speed at which we consume versus the rate of natural replenishment. On Mars, every one of these problems would be amplified. There would be no rain cycle to purify contaminated water naturally, no vast oceans to dilute pollutants, no biosphere to help process and recycle nutrients through natural systems. Mars would become a closed system where every mistake persists, where every ton of water wasted or contaminated diminishes the finite reserves we can never replace. Alternative approaches exist, of course. We could design water-conserving habitats, closed-loop systems where every drop is endlessly recycled. We could limit our presence to small, carefully managed colonies that treat Martian water as the sacred resource it truly is. We could commit to leaving the polar caps untouched, developing technologies that extract only what is absolutely necessary from subsurface ice, and doing so with such precision that contamination becomes impossible. We could establish zones where no industrial activity is ever permitted, preserving regions of Mars in their ancient state for scientific study and as a gesture of cosmic humility. But history suggests we would not choose these paths. The pressure to expand, to grow, to prove that terraforming works and justify the trillions invested, these forces would almost certainly override conservation. We would tell ourselves that we are being careful, that regulations are in place, that this time will be different. We would discover too late that Mars's water reserves were smaller than estimated, more difficult to extract than predicted, more vulnerable to loss than our models suggested. By the time the crisis became undeniable, we would have already consumed or contaminated a significant fraction of the planet's finite water supply. The water wars on Mars would not be fought with weapons. They would be fought with spreadsheets and extraction quotas, with political debates over acceptable loss rates, with economic models that discount long-term sustainability in favor of short-term gain. They would be wars against time, against physics, against the fundamental reality that Mars is not Earth and cannot be forced to become Earth. Without consequences, we are only beginning to understand. In destroying Mars's most precious resource, we would not merely be altering a planet, we would be proving that even when given a fresh start on a new world, humanity carries with it the same patterns that have brought Earth's ecosystems to the brink. The question is not whether we could terraform Mars, but whether we have the wisdom not to. As we contemplate the transformation of Mars, we must pause and turn our gaze inward, not toward the red planet, but toward ourselves. For this is not merely a question of technology or engineering. It is a mirror held up to humanity's oldest patterns, our deepest contradictions, and our most troubling tendencies. The story of terraforming Mars cannot be told without acknowledging the story of who we are, and more importantly, who we have been. History whispers to us across the centuries. When European ships first crossed vast oceans to distant shores, they carried not just explorers, but an ideology of transformation. Continents were renamed, ecosystems were re-engineered, indigenous peoples were displaced or destroyed, their existence deemed incompatible with the vision of progress. Forests that had stood for millennia were cleared, rivers were diverted, mountains were hollowed out for resources. All of this was done under the banner of civilization, of improvement, of making the land productive according to values imported from elsewhere. Mars presents us with a parallel so striking it cannot be ignored. Here too, we encounter a world that exists in its own right, shaped by processes older than human consciousness itself. Here too, we arrive with grand visions of transformation, of making the planet useful, of bending an entire world to serve human needs. The language we use reveals our intentions. We speak of colonizing Mars, terraforming it, making it Earth-like, as if Mars in its current state is somehow incomplete, somehow waiting for us to finish what nature left undone. But perhaps the deepest question is this: who decides? In the councils of nations and the boardrooms of corporations, plans are being drawn for Mars. Treaties are debated. Mining rights are discussed. Territorial claims are whispered in careful diplomatic language. Yet Mars itself has no representative. No voice speaks for the ancient canyons, the polar ice, the dust devils that dance across Syrtis Major. The planet that has existed for 4.5 billion years is suddenly subject to decisions made by a species that has existed for a fraction of that time. The Outer Space Treaty of 1967 declares that no nation can claim sovereignty over celestial bodies. Mars, it states, is the province of all mankind. Beautiful words, Yet even they carry an assumption that Mars exists for mankind, not for itself, not as an entity with intrinsic value, but as a resource, a frontier, a place that belongs to us by virtue of our ability to reach it. The ethics of planetary ownership become not just philosophical abstractions, but urgent legal and moral questions that will define the next chapter of human expansion. Already we see the fault lines forming. On one side stand those who view Mars primarily through the lens of preservation. To them, Mars is the greatest scientific treasure in human reach, an intact planetary laboratory where we can study climate, geology, and perhaps even the origins of life itself. They argue that transforming Mars would be an act of cosmic vandalism, destroying forever our ability to understand planetary evolution, to learn lessons that might even help us save Earth. On the other side stand those who see Mars as humanity's lifeboat, our insurance policy against extinction, a world waiting to be awakened to biological productivity. To them, preserving Mars in its current state is a luxury we cannot afford, a sentimental attachment that prioritizes rocks over human survival. But there is a third perspective emerging, one that sounds radical until you truly consider it. The Martian rights movement, still in its infancy, asks a question that previous generations would have found absurd. Should Mars have legal personhood? Should an entire planet have rights that must be considered before we alter it? It sounds like science fiction, yet consider that rivers, forests, and even ecosystems on Earth have been granted legal standing in some jurisdictions. New Zealand's Wanganui River is legally recognised as a living entity. If a river can have rights, why not a planet? This is not mere philosophical posturing. Legal personhood for Mars would fundamentally change how we approach its transformation. It would require us to demonstrate that terraforming serves not just human interests, but can somehow be reconciled with respecting Mars's intrinsic existence. It would demand environmental impact assessments on a planetary scale, conducted not just for human benefit, but for the planet itself. Some argue this is anthropomorphizing a dead world, projecting human concepts onto lifeless rock. Others counter that calling Mars dead is itself a human judgment, one that dismisses the complex geological processes, the seasonal cycles, the dynamic atmosphere that makes Mars very much an active, evolving world. Yet perhaps the most profound ethical dimension involves those who are not yet born. We are the first generation capable of reaching Mars, but we will not be the last. Thousands of years from now, assuming humanity survives, there will be scientists who wish they could study Mars as it was before we arrived. They will want to understand how planetary atmospheres evolve naturally over billions of years. They will want to search for evidence of ancient Martian life in strata we might contaminate or destroy. They will want to test theories about planetary formation using Mars as a pristine example. If we terraform Mars in the 21st or 22nd century, we steal that opportunity from every scientist who will ever live after us. We make a decision for all future generations based on the needs and desires of a single moment in human history. This is intergenerational ethics at its most stark. We are considering an irreversible act that will echo through all of human time. Unlike almost any other human project, terraforming cannot be undone. We cannot untransform a planet. If we make the wrong choice, there is no reset button. Future generations will inherit not the Mars that formed in the ancient solar nebula, but the Mars we created, shaped by technologies and priorities they had no voice in choosing. And here, we must confront the most uncomfortable truth. The driving forces behind Mars colonization are unlikely to be purely scientific or altruistic. Already, private companies speak of mining Mars for resources, of establishing property rights, of creating economic opportunities. The first serious attempts to alter Mars will likely be driven not by scientific consensus or careful ethical deliberation, but by corporate interests, by the pursuit of profit, by competition between nations seeking prestige and strategic advantage. History teaches us what happens when economic interests clash with preservation. On Earth, we have countless examples. Forests razed despite scientific warnings, oceans polluted despite knowing the consequences, species driven to extinction despite their irreplaceability. The pattern is depressingly consistent. Short-term economic gain triumphs over long-term ecological wisdom. Now we propose to take this pattern, this very human tendency, and export it to another world. What makes us think the outcome will be different? The conflict is not hypothetical, it is already forming. Companies plan mining operations, nations draft space resource legislation. The race is on, and Mars is the prize. Scientific voices calling for caution, for study, for preserving Mars as it is. These voices risk being drowned out by the momentum of commerce and national ambition. The same dynamic that has led to environmental catastrophe on Earth is being replicated in our approach to Mars, only this time on a planetary scale. Perhaps most troubling is the hubris embedded in the terraforming vision. We propose to engineer an entire planet's climate to fundamentally alter its atmosphere, to trigger geological processes, to create a biosphere. Yet we have not successfully managed Earth's climate. Our own planet's systems are spiraling beyond our control, despite decades of warnings. Ice caps melt, weather patterns shift, species vanish, and in the face of this failure, we propose to control Mars. The confidence required to believe we can successfully terraform another planet while we are actively de-terraforming our own is breathtaking. This reveals something profound about humanity's relationship with nature. We view the natural world not as something to live within, but as something to be managed, controlled, optimized. A mountain is not valuable as a mountain, but as a potential mine. A forest is not valuable as a forest, but as lumber and land. And now, Mars is not valuable as Mars, but as potential Earth. This utilitarian view has driven human progress and human destruction in equal measure. It has built civilizations and emptied oceans. Applied to Mars, it could achieve wonders or commit crimes on a scale never before possible. In the silence of space, Mars continues its ancient rotation, indifferent to our debates, unaware of our plans. The red sands shift in winds that have blown for eons. The seasons change according to patterns older than multicellular life. Mars simply is, has been, and would continue to be, with or without us. The question is not what we can do to Mars. We have already established that we likely possess the technical capability. The question is what we should do, what we have the right to do, what we have the wisdom to do. As we contemplate the transformation of an entire world, we must recognize that this is not just about Mars. It is about us. About whether we can evolve beyond the colonial impulse to transform everything we touch. About whether we can recognize value in preservation as well as exploitation. About whether we have learned anything from our history of environmental destruction or whether we will simply export those same patterns to new frontiers. Mars will survive regardless of what we decide. But what we decide about Mars may determine whether humanity survives its own power. Terraforming a planet is often drawn as a clean diagram. Arrows, timelines, milestones. First, we thicken the air. Then we warm the ground. Then we add water, plants, cities under soft blue skies. It looks orderly, linear, predictable. But nature does not operate in straight lines. It works in loops, feedbacks, delicate chains of cause and effect, where one small shift can ripple outward, amplifying into something vast and uncontrollable. On Earth, we see hints of this in our own climate system. Ice melts, revealing darker oceans that absorb more heat, which melts more ice. Forests burn, releasing carbon, which warms the air, which dries more forests. These are not isolated events. They are conversations between air, rock, water, and life. On Mars, we would be stepping into this conversation with a megaphone without truly understanding the language. In systems theory, there is a simple lesson. The more complex the system you try to control, the more surprising its failures become. A planet is the most complex system we know. It has no off switch, no reboot button. Every intervention, every mirror in orbit, every factory pumping out greenhouse gases, every redirected comet, does not just change one thing. It changes everything else that touches it, often in ways we never predicted. Imagine the unfolding of a single bad decision. We begin by releasing powerful greenhouse gases to warm Mars's thin, frozen atmosphere. For a time, it works beautifully. Temperatures creep upward. Dry ice caps at the poles begin to sublimate, releasing carbon dioxide and thickening the air. Dust storms grow more frequent, more energetic, lofting dark particles into the sky that soak up even more heat. The planet awakens. But with warmth comes volatility. The newly thickened atmosphere feeds larger global dust storms, the kind that can envelope the entire planet in a veil of rust for months. Those storms block sunlight, cooling the surface again. Temperature swings become extreme, weeks of gentle warming, followed by months of sudden dimming. The early infrastructure we've built, solar farms, fragile habitats, orbital shades carefully balanced to control climate, begins to strain under the chaos. A storm rips through a region where we've started seeding hardy engineered microbes into dark basalt plains, hoping they will fix nitrogen and slowly exhale oxygen over centuries. The storm doesn't just move dust. It redistributes those organisms, sweeping them into craters, valleys, subsurface ice deposits we barely mapped. Our carefully controlled biological experiment suddenly goes planetary. In one low-lying basin, those microbes find something unexpected. A brine pocket warmed by our earlier geothermal drilling, laced with perchlorates and primitive Martian organics we never fully catalogued. Chemical reactions we did not simulate begin to run. The microbes mutate, adapt, or die in ways that quietly rewrite the possibilities of the Martian biosphere. We do not notice until the air chemistry starts to drift. The oxygen we expected to rise remains stubbornly low. Methane spikes appear in the atmosphere, coming and going with the seasons, far more erratic than our models predicted. Some of that methane might be from our own industrial processes. Some might be biological. Some might be purely geological, released from clathrates and trapped reservoirs as the permafrost softens. But from Mars's perspective, the distinction doesn't matter. The system is changing, and it is changing faster than our equations can follow. To maintain control, we double down. More orbital mirrors, more greenhouse factories, more energy imported from space-based solar arrays and nuclear stations buried in the regolith. Each new layer of technology is meant as a stabilizer, but each also becomes another point of failure. A mirror knocked slightly out of alignment by micrometeorites focuses too much light on a polar region, triggering a rapid release of trapped CO2 and water vapor. A slight overcorrection in the other hemisphere leads to deep cold, preserving ice we needed to melt in order to complete our climate plan. Suddenly, Mars is no longer gradually warming. It is lurching between states. We enter what systems scientists call a regime shift, a tipping point where the planet's own feedback loops take over. Dust storms feed on themselves. Newly darkened surfaces accelerate heating. Permafrost collapse releases not just gases, but buried salts and toxic compounds into the thin waterways we coaxed into existence. A river that flowed tentatively for a few decades becomes a seasonal torrent of corrosive brine, poisoning experimental oases and early greenhouses along its banks. The dream of a red planet slowly turning blue fractures into patches of chaos. Some areas too cold, some too hot, some chemically hostile, some choked in permanent dusk under suspended dust. We thought we were painting a world. Instead, we were kicking a sleeping machine whose gears mesh across every layer of rock and sky. At some point, every scenario modelling team, every climate engineer on Mars and Earth begins to see the same pattern in their simulations. There is a line where interventions stop helping and start amplifying the chaos. That line is not drawn in the soil, it is drawn in time. We call it the point of no return. There comes a moment when too many of Mars's original conditions have been erased to easily recover, but too few of our desired conditions have stabilized to make it a truly habitable world. The native atmosphere has been altered. Ice reservoirs have been redistributed, refrozen, sublimated, or chemically bound. Any indigenous microbes, if they existed, have been stressed, displaced, or annihilated. Our engineered organisms, designed for a narrow range of conditions, begin to fail as the environment swerves beyond their tolerance. Mars is no longer the planet we found, but it is not the planet we intended either. Could we simply undo our mistakes? In science fiction, there is often a comforting notion. If we go too far, we can reverse course. Shut down the factories, turn off the mirrors, refreeze the poles, re-terraform, Mars back to something like its original state. But the universe is built on irreversibility. Every gas molecule released into the air, every ice deposit melted and refrozen in a new layer, every microbe that mutated, every chemical weathering cycle we accelerated. These are not beads on a string we can slide back into place. They are history written into the rocks, the atmosphere, and whatever passes for soil on Mars. On Earth, even stopping all emissions today would not instantly reset the climate. Oceans would continue to warm for decades. Ice sheets would keep responding for centuries. The long memory of a planet is written in slow processes, not quick switches. Mars would be no different. In fact, with its thinner atmosphere and fragile, volatile reservoirs, it might be even less forgiving. Our backup plans begin to look less like strategies and more like wishful thinking. Some proposals might involve installing vast sunshades at the Mars-Sun L1 point to dim the planet back down. Others might suggest using giant mass drivers to loft excess atmosphere into space, slowly bleeding off pressure we regret adding. But these ideas run headfirst into physics and economics. By the time we recognize the full extent of the cascading failures, we would have sunk not billions, but tens of trillions of dollars, decades of work, and perhaps millions of lives into the Martian project. Entire industries across Earth and Mars would depend on its continuation. Mining, construction, off-world manufacturing, data, energy. Stopping would not just mean scientific disappointment, it would mean economic shockwaves reverberating through two worlds. Supply chains built around Martian exports would snap. Debt structures linked to terraforming outcomes would implode. Nations and corporations that stake their future on Martian real estate would face ruin. And as with any large-scale collapse, those with the least power would bear the harshest consequences. Workers stranded in half-finished Martian settlements, communities on Earth whose livelihoods depend on orbital infrastructure now rendered obsolete. In that pressure cooker, the instinct will not be to stop. It will be to push harder. More investment, more emergency measures, more radical engineering in the hope that one last breakthrough will turn the tumbling system upright. But in systems theory, this is exactly how complex projects die, not from a single failure, but from layers of fixes that interact in unpredictable ways. We risk creating something worse than the Mars we began with. A planet with a thicker, dust-laden atmosphere that erodes electronics and lungs alike. Temperatures just warm enough to mobilize toxic salts and heavy metals, but not stable enough to sustain open, clean water. An alien biosphere, partly engineered, partly accidental, filled with hardy extremophiles optimized for survival, not for compatibility with human health. A world that is, in some ways, harsher than the original Mars, because it is unstable. And in the same gesture, we could create something worse than Earth. Not in beauty or biodiversity, but in the precedent it sets. That faced with the difficulty of repairing one damaged biosphere, we chose to experiment on another and misjudged the stakes. Yet even in this bleak scenario, there is something quietly important. Cascading failures are not just stories of collapse, they are maps of connection. They reveal how tightly everything is woven together. Ice to air, rock to water, economics to ethics, ambition to humility. If we listen to what those failures are telling us, they might not just warn us about Mars. They might illuminate something about our own planet, the only one we currently inhabit, the only one we truly understand, and the only one we have already begun to terraform by accident. If the ethical questions of terraforming Mars feel distant, abstract, or debatable, this part is not. Because beyond philosophy and politics, Mars is already something of staggering value to humanity. It is a laboratory, not one we built with steel and glass, but one carved in basalt and ice, written in craters and dried riverbeds. A lab that has been running a single exquisite experiment for over 4 billion years. What happens to a rocky, potentially habitable world when it fails? Mars is not just another planet. It is the closest parallel case study to Earth we will ever have. Same neighborhood, similar building blocks. A history that began with warmth, liquid water, and perhaps the chemistry of life, and then diverged. Terraforming Mars doesn't just change that story, it overwrites the data. It is the scientific equivalent of taking the only copy of a priceless, ongoing experiment and pouring it down the drain. When we look at Mars today, we are not just seeing red dust and dead rocks. We are seeing time, fossilized, ancient valley networks, delta fans, sedimentary layers stacked like pages of a planetary diary, minerals that can only form in neutral water, salts that record the retreat of ancient lakes, clays that formed when the planet was warmer, wetter, and perhaps alive with chemistry we are only beginning to understand, volcanic plains that speak of a once active interior, polar caps that silently tally the cycles of Martian climate like rings in a cosmic tree. Terraforming, by definition, aims to erase that environment and replace it with something new. We would erode, melt, sublimate, and chemically alter the very structures that hold Mars's memories. Atmospheres thickened, ice caps vaporized, permafrost destabilized, entire regions flooded or chemically reshaped. In a few thousand years, or even just a few centuries, the original signals we came to study would be buried beneath our own engineering. When we talk about losing Mars, it's not just poetic language. We would lose a continuous geological record that spans nearly the full age of the solar system. On Earth, plate tectonics and erosion have recycled most of our planet's ancient crust. The first billion years of Earth's history are almost entirely gone, ground down, subducted, remelted. On Mars they remain, preserved in old highlands, impact basins, and cratered terrains that have been sitting in thin air, barely weathered, for eons. Mars is a museum of planetary adolescence. Every dried riverbed is a record of early climate. Every layered deposit is a snapshot of shifting atmospheres, tilts, and ice ages. Every buried glacier is a frozen archive of dust, ice, and trapped gases that could tell us how a once potentially habitable world slowly choked, cooled, and froze. The moment we begin to radically alter the Martian environment, we begin to scramble those records. Flooding lowlands with artificially released water could wash away sediments that have lain undisturbed for billions of years. Warming polar caps to create an atmosphere would erase delicate stratifications that encode hundreds of thousands, maybe millions, of years of climate cycles. Injecting greenhouse gases or altering dust content could contaminate the very signals future scientists might hope to read. We would be taking a nearly pristine control sample of planetary evolution and turning it into a laboratory spill. For scientists trying to understand Earth, not as it is, but as it was, and as it might become, Mars is more than interesting. It is essential. Our own planet is messy. Life has transformed the air, the oceans, the rocks themselves. Tectonic plates constantly recycle old crust into new. Weather erases and rewrites the landscape at a dizzying pace. Signals from the distant past are faint, incomplete, stitched together from fragments. Mars is different. It stalled early, its core quieted, its magnetic field faded, its atmosphere thinned, water retreated into the ground and the poles. And then, it just kept existing, like a paused simulation, allowing us to walk backward through time by reading its surface. To understand Earth's earliest oceans, we can study Martian lake beds. To model Earth's ancient skies, we can measure Martian minerals, isotopes, and ancient weathering patterns. To forecast how planets lose atmospheres and magnetic protection, we can watch Mars today as solar winds strip away its remaining gases. Every crater rim, every battered plateau, every deposit of salts or sulfates is another clue about how worlds live and how they die. Terraforming Mars replaces those clues with noise, our noise. Imagine trying to study natural climate change on a planet where you just detonated a planetary-scale geoengineering project. Distinguishing what Mars did on its own from what we forced it to do would become almost impossible. Subtle patterns would be blurred. Signals that might have led to breakthroughs in understanding planetary habitability would be buried under a fast-forwarded, noisy rewrite. There is another loss that is easy to underestimate: the loss of comparison. In planetary science, one planet is interesting. Two planets are a pattern. Earth and Mars form a pair, sister worlds that began with overlapping conditions and then diverged dramatically. One became blue and teeming, the other turned red and barren. That divergence is one of the most powerful natural experiments the universe has given us. Change Mars to be more like Earth, and we collapse that experiment. We go from a two-point comparison, Earth and a failed Earth, to a single point, Earth and Earth, with training wheels, both shaped by the same species, the same technology, the same mistakes. Without pristine Mars, our ability to do comparative planetology at close range evaporates. We lose the ability to test theories about: why did Mars lose its water while Earth kept hers? How crucial is a strong magnetic field? How do different planetary sizes and internal heat budgets affect long-term habitability? What does a planet look like after it crosses a tipping point and never comes back? Those aren't just questions about Mars. They are questions about us, and about every habitable world we may one day find orbiting other stars. And then there is climate. Mars is a living natural experiment in atmosphere loss, dust-driven weather, polar cycles, and runaway cooling. Its thin air, carbon dioxide-dominated sky, and active dust storms offer a parallel case study to Earth's climate systems. One, stripped of oceans and forests, simplified but revealing. By reading its rocks and ices, we can ask, how fast can a planet's climate change? What combinations of volcanic activity, asteroid impacts, solar evolution, and internal cooling can push a world from warm and wet to cold and dry? How do small changes at the top of an atmosphere cascade through an entire planetary system? Climate scientists already use Mars as a testbed for our models. The more precisely we can reconstruct its past, the better we can understand the boundaries of stability on Earth. How close can we approach certain thresholds before we risk long-term, irreversible shifts? Terraforming Mars in the name of making a second home might sound like an insurance policy for humanity. But scientifically, it could rob us of information that helps us keep our first home livable. That's why some planetary scientists, astrobiologists, and ethicists argue that Mars may be more valuable untouched than transformed. Not because they are against exploration, not because they dislike the dream of other worlds, but because they recognize that Mars, as it is now, is a once-in-a-civilization asset, an entire planet-sized archive, waiting to be read with tools that don't yet exist, by generations of scientists not yet born. You and I live very early in the story of space exploration. Our instruments are crude compared to what will come. Our drilling is shallow. Our rovers crawl at walking speed. The data we gather from Mars today is extraordinary, but it is a first draft, not the final word. To terraform Mars in the near future would be like walking into an ancient library, glancing at a few shelves, and then deciding to burn the rest for warmth. Some will argue that transformation itself can be a new experiment, that watching how a cold, dead world responds to our interventions is also data, that by changing Mars, We learn different things, perhaps even things that help us manage Earth. There is some truth in that, but we have only one untouched, rocky neighbour that began like us and ended differently. Only one world where we can see what happens when habitability slips away without the influence of an industrial civilization. We will never again find a version of Mars in our past, and once we change it, we cannot unchange it. Preserving Mars as a scientific sanctuary is not about denying humanity a new home. It is about questioning the timing, the pace, and the cost. It is about asking whether a patient, careful approach, one that prioritizes understanding before transformation, might serve us better in the long run. Because what we stand to gain from an untouched Mars is not just knowledge of rocks and ice and atmospheres. We stand to gain a deeper understanding of how fragile habitability is, how unique or common our own story might be, how planetary environments tip and topple, and how close we might be to doing the same. In that sense, preservation is not an act of restraint for its own sake. It is an investment in our future, a recognition that this rust-red world, silent and cold, may yet be our greatest teacher, and that in our eagerness to make it more like home, we risk silencing a voice we have only just begun to hear. We leave behind the vision of a red world swallowed by our ambition and drift, for a moment, into a quieter orbit of possibility. The nightmare of planetary scale transformation is not the only future we can imagine. There are gentler paths, slower paths, futures where Mars is not conquered, but carefully, deliberately approached, like a fragile artifact in a museum, not a blank canvas for our impatience. In the thin light above Mars, another idea begins to take shape. Instead of changing an entire planet, we change the scale of our dreams. This is the promise of para-terraforming. Rather than releasing oceans of greenhouse gases into the Martian sky, rather than thickening the atmosphere until the whole world gasps under our hand, we build worlds inside worlds. Giant domes, buried caverns, cliffs sealed with transparent roofs, islands of Earth-like environment, suspended in a Martian sea of cold, thin air. Imagine standing at the edge of Valles Marineris, not under an open blue sky we manufactured, but beneath a vaulted glass canopy anchored into the canyon walls. Outside the dome, the landscape remains unchanged. Rusted rock, ancient dust, the silence of a world preserved. Inside, plants breathe out oxygen. Rivers, small but real, cut tiny paths through imported soil. Gravity is still Mars's own, but the air, the pressure, the warmth are crafted and contained. Para-terraforming asks a different question. Instead of forcing Mars to carry all of us, can we learn to live in carefully carved pockets that respect the planet's original state? Under ice sheets at the poles, where thick layers of frozen water and dust can shield inhabitants from radiation, we build cavernous habitats lit by artificial suns. On the flanks of extinct volcanoes, we inflate kilometre-wide pressure spheres anchored with cables and regolith. In subsurface lava tubes, natural tunnels stretching for miles, we create cities that never touch the surface sky. Outside, Mars remains Mars. Its atmosphere stays thin. Its chemistry stays alien. If there is life in the soil, it still has somewhere to exist undisturbed. These enclosed worlds become laboratories of restraint. We test crops, closed-loop life support, new ecologies, knowing that if something fails, it fails within walls, not across an entire planet. Para-terraforming is not just a technical compromise. It is a moral one. It says, we can be here, but we do not have to overwrite everything that was here first. Yet there is an even more radical thought waiting in the dim hallways beneath these domes. What if, instead of reshaping planets to fit us, we reshape ourselves to fit the planets? On Earth, life has rewritten its own design over billions of years. Fish became creatures that walk on land. Forest plants learned to live in deserts. Tiny bacteria adapted to boiling hot springs, nuclear reactors, and the crushing dark of the deep ocean. We are the first species that can guide that process with intent. Bioforming, adapting humans and our companion life to alien environments, offers a mirror image of terraforming. Instead of thickening Mars's air, we modify our lungs and blood to live with lower pressure. Instead of raising the temperature of the entire planet, we adjust our metabolism and clothing to endure more cold. We engineer microbes that can coexist peacefully with Martian chemistry, not steamroll it. Imagine future humans whose bones are shaped by 0.38 g from birth, whose muscles grow optimized for low gravity, whose vision is tuned to the dusty red of the Martian horizon. Humans with enhanced resistance to radiation, not because Mars is dangerous, but because space is. Humans who can sleep in cycles matched to Martian days and Earth days alike. Bioforming raises profound questions. At what point are we still human? Who decides what changes are acceptable? But it also shifts the burden of adaptation. Instead of demanding that an entire planet give us what we already have on Earth, we choose to evolve, culturally, biologically, technologically, to meet the universe where it is. Between these ideas, para-terraforming from the outside, bioforming from the inside, a new proposal emerges. Perhaps Mars does not have to be a colony at all. Perhaps it can be a museum, not a museum in the sense of glass cases and velvet ropes, but a planetary-scale archive, a place where we agree in advance to do less. In the Museum Mars proposal, Mars becomes a mostly preserved world. We allow research stations, carefully shielded habitats, and minimal surface footprints. But the vast majority of the planet is left untouched. No global warming schemes, no massive atmospheric engineering, no seas poured into ancient basins. We come here to learn, not to own. Humanity still grows outward, but it focuses its heavy industry, its large-scale settlements, on places that are already chaotic and transformed. Resource-rich asteroids, radiation-bathed moons, and free-floating habitats constructed from raw material in space. Perhaps large colonies form in the shadow of Phobos and Deimos, Mars's tiny moons. Perhaps we hollow out chunks of the asteroid belt or build spinning cylinders in orbit, with landscapes on their inner walls and stars on the outside. In these places, the ethical tension of altering a potentially living planet is less sharp. We work mostly with rock and ice, not with the delicate possibility of alien biology. Mars, meanwhile, becomes a controlled experiment that never ends. We track its seasons for centuries. We map its magnetic history, its atmosphere, its underground ice. We search for life with methods so careful they leave barely a footprint. Just as national parks on Earth preserve entire ecosystems from being paved over, Museum Mars preserves a whole world before we fully understand what it is. This approach depends on a different kind of technology, one that does not aim to dominate Mars, but to coexist with it. Instead of planet-wide mirrors, we deploy small targeted sunshades to keep local habitats stable without altering the global climate. Instead of pumping greenhouse gases into the sky, We recycle every molecule of air and water in closed systems with near-perfect efficiency. Our power comes from high-altitude solar arrays, nuclear reactors buried deep for safety, or even future fusion systems that require minimal surface disturbance. Rovers and drones travel sterilized, then re-sterilized, then monitored, as if each one were a rare surgical instrument. Airlocks become rituals of containment. Dust is not just a nuisance, it is a sample, a record, a potential carrier of something ancient and alive. We turn our technology inward, building smarter life support, better recycling, more resilient habitats, instead of reaching outward with crude atmospheric engines that treat the whole planet as a single machine. This kind of restraint is not something our species has practiced well on Earth. We drained rivers to feed cities. We raised forests to grow food. We mined, burned, and spilled our way into a climate we now struggle to control. Mars offers us an uncomfortable chance to look at another world and ask, will we repeat the same pattern, only faster? Learning from Earth means recognizing that environmental impact often feels reversible until it isn't. On our home planet, ice sheets do not regrow on human timescales. Extinct species do not return. Coral reefs do not spontaneously rebuild after centuries of damage. We speak of restoration, but what we usually mean is adaptation to a changed baseline. On Mars, a single large miscalculation, warming that outruns our control, chemical reactions we didn't predict, contamination that spreads through subsurface brines, could lock the planet into a new state for millions of years. There is no urgent native civilization here to protest. But the absence of voices does not mean the absence of value. So we consider a different strategy: colonization that is minimal, reversible, and always open to the possibility of stepping back. Reversible colonization does not mean we can erase every trace of our presence, but it does mean designing our footprints to fade instead of deepen. Structures that can be dismantled or abandoned without cascading planetary changes. Nuclear waste stored in orbits that can be adjusted rather than buried irretrievably in Martian soil. Industrial activity limited to orbital factories using asteroid material, not Martian bedrock. If, a century from now, we discover that Mars hosts fragile subsurface life easily disrupted by our presence, a reversible approach would allow us to retreat, to scale back to research stations, to relocate large settlements off-world, to keep Mars mostly as it was. This is not a call for paralysis, but for patience. In a universe that has existed for over 13 billion years, waiting another 100 or 200 years before we attempt irreversible planetary engineering is not caution to the point of cowardice. It is humility proportional to the timescale of the cosmos. During that time, our tools will evolve. Our genetic engineering will become more precise, our life support systems more efficient. Our understanding of Mars, its climate, its geology, its potential biosphere, will deepen. With each passing decade, the odds that we make fewer, less catastrophic mistakes increase. Rushing to terraform Mars today is like rewriting an ancient manuscript in ink before we've learned to read the language. We might be painting over something we don't yet know how to recognize. Alternatives to full-scale terraforming do not take away the dream of Mars. They refine it. They invite us to imagine a future where domes glimmer faintly in the polar twilight, where orbiting habitats spin slowly over canyons untouched by human boots, where laboratories beneath the surface listen for the faintest whisper of alien metabolism. A future where humanity spreads to the stars not as a force of erasure, but as a patient observer, a cautious participant, and, when we have earned it, a careful shaper. Mars does not demand that we choose between absence and domination. It offers us a quieter third path, presence without planetary murder, curiosity without conquest, progress without the need to turn an entire world into a monument to our impatience. On that path, hope is not found in how quickly we can make Mars look like Earth. It is found in whether we can learn, at last, to live in a universe that does not owe us anything, and to thrive there anyway. We have wandered across an imaginary Mars tonight, not the quiet, rust-red world that circles our sun in silence, but a reshaped planet, thick with artificial air, flooded with melted ice, stirred by machines and human ambition. Along the way, we have seen the shadows that follow the dream. We watched an engineered atmosphere turn violent, a fragile sky whipped into chaos by forces we only half understand. We walked across a crust awakened from its long sleep, its buried stresses and ancient fractures pushed into motion by our own hands. We stood at the edge of invisible ecosystems, microbial worlds that might exist beneath the ice and dust, and realized that to terraform Mars could mean erasing an entire lineage of life before we ever knew its name. We saw water, Mars's most precious treasure, mined, boiled, redirected, wasted. Not as a sacred resource, but as raw material in a planetary scale experiment. And we confronted a more uncomfortable truth, that wherever humans go, we carry not only curiosity and courage, but also power, hierarchy, and history. The idea of making Mars like Earth began to look less like exploration and more like the extension of very old patterns, extraction, ownership, control. In the end, everything wove together into a single unsettling picture, a cascade of failures. Atmospheric systems reacting in ways models did not predict, geology amplifying our mistakes, biology, ours and anything native, caught in the crossfire, and above all, the loss of Mars itself as a scientific time capsule, a pristine record of planetary evolution sacrificed for a future we are not obligated to choose. All of this leads to a question that feels larger than Mars. Are we wise enough for planetary engineering? We know how to talk about rockets, launch windows, and payloads. We are good at countdowns and first steps, but terraforming is not a launch. It is not a mission. It is a commitment that unfolds over centuries, across generations that will inherit decisions they never had the chance to make. Perhaps the most important technology we need is not a new reactor or a better regolith processor, but patience. The ability to say, "We don't know yet. Let's understand this world before we rewrite it." This is why these conversations matter now, while Mars is still untouched by our machines on a global scale, before treaties are rewritten, before industrial contracts are signed, before, of course, we'll terraform it, hardens from a sci-fi slogan into an unquestioned assumption. The stories we tell about Mars today will shape the policies, the funding, and the ethics of tomorrow. That includes this story you're listening to right now, wherever you are in the world. If this journey kept you company tonight, you can gently help it reach others. You can like this video, subscribe to the channel, and let the algorithm know that slow, careful thinking about big questions is still worth amplifying. And if you feel like sharing a small piece of your own world, let me know in the comments where you're listening from. What corner of this one habitable planet is your vantage point as we imagine another? For those who want to support these long, quiet explorations a bit more, there's an optional YouTube membership. It's never expected, but always appreciated. Simply being here, listening, and thinking deeply already matters. Because in the end, Mars is not just a distant world, it is a mirror. When we decide what we are willing to do to another planet, we reveal what we believe about our own. Will we rush to remake Mars in our image? Or will we learn, for the first time in our history, how to live in a universe full of worlds without needing to own and alter them? That choice has not been made yet. It is still ahead of us, waiting quietly on the red horizon.